Okay, welcome everyone. So far we've been taking a look at what effect, if any, does applying an elementary row operation to a matrix have on the determinant of the resulting matrix. So we've seen that when we do a scaling operation that scales the determinant, when we do an interchange of two rows, that changes the sign of the determinant. So what we'll take a look at here is the last point, that is, if we apply a row replacement operation to matrix A and wind up with matrix B, then these two matrices, A, the matrix we started with, B, the matrix we get after doing the replacement operation, those two matrices are going to have the same determinant. So in other words, applying a row replacement operation to a matrix has no effect on the determinant of the resulting matrix. So we'll prove this similar to how we worked through interchange. So in particular, we'll start with the n equals 2 case and then work our way up to the n equals 3 case and kind of show that once we show it's true for n equals 2, that's going to imply that it follows for n equals 3 and n equals 4 and for any value of n, no matter how large. So if we have a 2 by 2 matrix over here, whose top row is AB and whose second row is CD, then we know the determinant of this matrix, we can call this matrix A, would be AD minus BC. And so now let's consider what happens if I do a replacement operation. Say I replace row 2 of matrix A with some scalar K times the first row plus the second row. So if I multiply the top row of matrix A by K and then add it to row 2, the new row that I would replace the original row 2 with would be C plus K times A plus, and then the second entry in row 2 would now be D plus K times B. And now we can calculate the determinant of this matrix by saying it's going to be A times D plus KB minus B times C plus KA. And now you can see that on the first term, we're going to get a positive A times K times B. From the second term, we're going to get a negative B times K times A. So these two terms cancel, and all that's left over is exactly the same derivative that we had initially, which is namely AD minus BC. So over here, we can see that when we did a replacement operation, regardless of what K is, on the second row, it did not affect the determinant at all. And you can similarly do a row replacement, say on row 1, and verify that this is also going to not affect the determinant at all. So any row replacement that I apply to a 2 by 2 matrix, we now can see that is not going to have any effect on the determinant. Okay, so now let's see what happens when we jump up to the next size, namely a 3 by 3 matrix. So now I've got some matrix A that I've written out below, just the general form. And for example, I could calculate the determinant of this matrix using a cofactor expansion across the third row, and that would look like A31 times cofactor 3,1 plus A32 times cofactor 3,2 plus A33 times cofactor 3,3. And in particular, cofactor, for example, 3,1, that would look like the determinant of the matrix A12, A13, A22, A23. Okay, where here we don't have a negative sign because the 3,1 position, 3 plus 1 is even, so we have a minus 1 to an even power. That's why we have a plus in front of this. And now let's consider the following replacement operation that we can do on matrix A. I'm going to replace row 2 of this matrix with row 2 plus some scalar K times row 1. So that's going to give us a matrix that I have below, where here K could be any scalar. And I'm going to just do this considering what happens if I did a row replacement on row 2 using some combination of row 1. And we could similarly show that this property is going to hold no matter what sort of row replacement operation we did on this matrix. So I'm just going to consider this replacement operation, namely replacing row 2 with row 2 plus k times row 1, and whatever replacement operation you wanted to construct, you could prove that it won't change the derivative, similar to how this one will follow. So here, let me do a cofactor expansion across row 3 again on this new matrix that we get after doing this row replacement. And what we'll see is that we're going to get the same exact expression back. And the reason why is, let's take a look what happens in the first cofactor. I'm going to take A31, which is the same as the original A31 because we didn't do any replacement or change row 3 at all. And now this cofactor in this new matrix below is exactly a row replacement of the cofactor from the first matrix that we had. And now we've already proven that for n equals 2, a row replacement does not change the determinant. So therefore, the determinant of this matrix that we have below with this row replacement is going to be exactly the same as the determinant of the matrix that we had originally with A. So all of these cofactors are all just row replacements of the cofactors that we had up here. So their determinants are not going to change. So the values of these cofactors are not going to change. So therefore, the determinant of this matrix A up top is exactly equal to the determinant of the matrix that we have below after doing that row operation. So here we can see that row replacement has no effect on the determinant of the matrix.